So in this lecture, we are going to learn about data modeling with relational databases and focus specifically on data modeling with PostgreSQL. So let's kick off things with a brief discussion about what PostgreSQL is and why it might be a fantastic choice for meeting our data platform requirements. PostgreSQL, or simply Postgres, is a robust relational database management system, or RDBMS. According to the folks at db-engines.com, it ranks as the fourth most popular database system in the world, just behind industry powerhouses like Oracle, MySQL, and Microsoft SQL Server. But unlike those three platforms, Postgres has already seen a steady increase in popularity over the last 6 years. This trend in popularity could be attributed to a number of different factors. First, PostgreSQL is an open source project, which makes it free for any organization of any size to pick up and apply to their needs. Compare that with some of the other platforms that can cost thousands or hundreds of thousands of dollars to deploy across the organization. You will see why PostgreSQL is a good choice from a simple financial perspective. Secondly, Postgres has been in active development for over 30 years. It has gained reputation for being a reliable, robust, and secure data platform. This is in large part due to its nature as an open source project where people from all over the world collaborate to examine source code, help identify and fix bugs, and develop new features. Finally, as more large businesses push Postgres to its limits, it gives smaller users more confidence in the platform's capability, which makes transitioning from a paid commercial database platform even more justifiable. After all, if organizations the size of Reddit, Apple, and Yahoo trust Postgres to meet their needs, then it's definitely up to the task of handling anything that I could throw at it. Now I mentioned that Postgres was a relational database management system. So let's unpack what that really means. An RDBMS creates a protective wrapper around your data. It gives your data a place to live, controls how it gets entered, and under what circumstances it should be modified or deleted. The RDBMS also secures your data and ensures that only people in applications that have expressed permission to view and change the data have the ability to do so, and keeps everyone else locked out. Finally, an RDBMS manages the performance of the system, which helps you enter data and retrieve information in the most efficient way possible. To do all of this, Postgres uses a server client model. The Postgres server handles the storage, security, and maintenance of your data by storing it in a container called the database. Each Postgres server can hold many different databases. A client application is then connected to the server so that end users can input data, modify that data, and then retrieve that data back out again. The beauty of this arrangement is that the server can exist on a centralized computer that provides a single point of contact for all different users in an organization. Then each user uses their own desktop computer running their own client application to access that shared resource pool. In this way, everyone across the organization is getting the same information, updating the same data tables, and viewing the same detailed reports. In order to perform all the tasks that a PostgreSQL server needs to do in order to manage your data, you'll need to be familiar with some of the SQL programming language. So SQL stands for Structured Query Language, and it's a common language used by data science professionals in practically every database application in use today. This makes the ability to read and write SQL commands a very transferable skill that's highly sought after in the workforce. Unlike many traditional programming languages, SQL uses human-readable syntax that's straightforward and flexible. So that's the basics of what PostgreSQL does and how it can be used to help protect and store your valuable data. Now I have provided you with the information on how to install PostgreSQL. So hopefully you don't face any issues in that. So now that you have got your PostgreSQL installed, let's get started with our demos. So we are going to be focusing on using Jupyter notebooks and using Python wrappers to execute our queries. And all of these queries, you are able to do them in just either PostgreSQL shell, but we are going to focus on utilizing a Python wrapper for these. But before we do anything in our Jupyter notebooks, let's go to pgadmin and let's start our Postgres server. And then we'll create a dummy database. So as you can see, here we are in the pgadmin interface, and this browser will open up automatically once you start the pgadmin. So we will right click on databases and then create a new database, studentdb. So as you can see, I have created this database. So now let's go back again to our Jupyter notebook. And so you don't want to close your pgadmin, let it be running in the background and do not close it. So we are back here in our notebook, and actually I'm just going to talk about something that you may come across when you are working on PostgreSQL, and it's about auto commits. So in this case, we are going to use this Python package here, and our wrapper is called psychopg2, and this is the Python package that wraps around PostgreSQL. So we have imported it in cell 1. Now let's create a connection to our database here in cell 2. So this connects in my case to a local instance of PostgreSQL. From there, we are going to use this database or schema, which in this case is the studentdb, which we have just created. And then it will be my username and password. So for my case, the user is Postgres and the password is my first name. So this connection will connect the database and ensure that you have the correct privileges to connect to the database. So now in cell 3, let's use the connection to get a cursor, and we'll use that to execute our queries. So we have our cursor now. Let's move on to cell 4. So in cell 4, we'll actually try to run a query, and so we'll do a select star from test. Now we see that we have got an error which says relation test does not exist, and this is because we have not created a table as yet. So we had expected this error, and that's why we are getting it. But that's fine. Let's go and fix this error. So in cell 5, let's create a table called test, and this is just an example. So I have 3 columns and they are all ints, and if I run this, I'm going to get another error. The error says current transaction is aborted, commands ignored until end of transaction block. And so this is not what I was expecting at all. So when you are using PostgreSQL, what we need to make sure that we understand is that we are working with an ACID database, and we need to make sure that we commit our transactions. So when I have that error in my query, I did not commit my transaction, and that is why I got an error. So as we have not committed the transaction, we had an error in our transaction block. At this point, we are blocked until we restart the connection, or we could have committed the transaction, so either one of those. So let's get our connection again in cell 6. So here we are going to connect to our database, and then we are going to get our cursor back. So in these exercises, the point of this demo is, instead of worrying about committing after each transaction or getting that strange error that we just saw, let's just set auto commit to true. So now in cell 7, you can see that I have set auto commit is equal to true. So what this says that after each call during the session, commit that one action and do not hold open a transaction for any other actions. So one action will be equal to one transaction. So for this demo, we are going to set auto commit in the session to true. And so we won't have to call connection.commit for each command. So now let's come to cell 8. Let's create a table test, and we have 3 columns inside it. And so when we execute it, we see that it executed perfectly. And we see that when we execute this code again with auto commit set to true, we didn't face any issues with the transaction blocks and we did not need to restart our connection. So let's come to cell 9 and we'll do a select star from test. And since we don't have any data inside our table, we are not going to get anything back. So we can check that in cell 10. Let's do a select count star from test. And this should return 0. And this is because we didn't insert any data in our table. So then let's just drop the table in cell 11. So this was just a demo to make sure that you understand why we are auto committing at each one of our demos. And so finally in cell 12, we will close our cursor and the connection to Postgres. So from here, we move on to our next notebook. This is all about creating a table in PostgreSQL. In this notebook, we are going to walk through the basics of creating a table in Postgres, inserting rows of data, and doing a simple query to validate that information. So in cell 1, we are going to import the library, and again, if an error pops up, make sure that you read it thoroughly, but it may be something that you can ignore. So that's fine. Now let's create a connection to our database in cell 2. This connects to our local instance, in our case of Postgres, and from there we'll use the database studentdb and the schema. So this connection will reach out to the database and ensure that we have the correct privileges to connect to this database. So I just want to let you know that here, this block of code that you're seeing is going to be pretty standard in all our notebooks. We are just adding this try and except to make sure that we catch the errors and that they are understood properly. This is just a good coding technique and a good practice to have. So we need to have that just to make sure that we are catching any errors, but what we really want to focus is on the try command. The rest is just pretty standard and we'll be using it again and again. So now let's come to cell 3 and this will help us make our connection. And next we are going to use that connection to get a cursor so that we can use that cursor to execute our queries. Now let's come to cell 4 and here we are doing auto commit is equal to true, and what this will do is for each action we won't have to call connection.commit again and again. The ability to roll back and commit transactions are a feature of relational databases. So in cell 5, let's actually create a new database, and here we are going to create student1. So now let's come to cell 6 and here we are going to close our connection to the default studentdb database and we'll reconnect to our student1 database and we'll get a new cursor. And as you can see here that we are going to close the connection and from there we'll connect to our new student1 database and then we are going to set our cursor. So all of these things are happening in this same cell and then at last we will set our auto commit is equal to true. And all this will work successfully. And so once we've done that work up front, let's actually start thinking about our table. So imagine that we are going to start creating a music library of albums. Each album has a lot of information that we could add. But we'll just start with album name, artist name and year. And we are going to call our table music library. This type of table that we want to create and the columns that we need really seem very natural to us. So let's imagine that our table name is going to be music_library. We are going to have 3 columns. One, album name. The second one is artist name and the third is year. So now we want to translate this into a create table statement. So let's come to cell 7 and again in our try catch block, we are going to create a table if it does not exist. So what this means is if the table does not already exist, create it. And if it already exists, don't create it. And we are going to call our table music library and then we are going to have 3 columns. So the album name will be varchar, the artist name will also be varchar and the year will be of int type. So now let's come to cell 8 and we will insert data into our tables. So I really want you to note the syntax of how we are doing this insert statement, because you will be doing it again and again throughout our exercises. So this is the syntax that you are going to use. So we are going to insert into music library, and then we are going to list our columns, and then we are going to list our values, and we are going to use this percent sign with an S, and then we are going to add comma, and then we are going to add in each one of the actual values. So in this case, we have a music library and we add in the details, and we are going to do the same thing for another row also. So we are going to insert 2 rows in total. Now let's come to cell 9 and validate if our data was entered successfully. So we are going to do a while loop over here, and we are going to use that for printing the results. If you were executing this query in the PostGRE SQL shell, you wouldn't need to write the while loop. But in this case, we are writing it because we are utilizing the Python library. Also, just a note here. So if you end up running the insert statements in cell 8 more than once, you are actually going to see duplicates in your data. So just to let you know that PostGRE SQL allows for duplicates. So now, finally in cell 9, we are going to do a select star from music library, and we are able to print the results. And so we can see here that our data has been successfully loaded into the music library. And then in cell 10, we are finally going to close out our connection to the database. So that is the end of this part. Now let's talk about data modeling with relational databases. Here you will be learning the fundamentals of how to do relational data modeling by focusing on normalization, denormalization, fact tables, dimension tables, and different schema models. Again, I just want to make sure that everyone knows that you really want to have a strong understanding of normalization and denormalization. Those are the heaviest topics that we are going to discuss today. So really, make sure that you take the time to understand these topics fully. So first, we are going to go through a bit of definitions and history before we get into some of the fundamentals that we are going to talk about. So let's start with a few definitions to make sure that we are all on the same page. A database is a set of related data and the way it is organized. Access to the data is usually provided by a database management system. So what is a database management system? This consists of computer software that allows us to interact with the database and provides access to all of that data. Because of the close relationship, the term database is often used to refer to both database and the database management system. So let's talk about the importance of relational databases. So a little bit of history here. The concept of relational databases was invented in about 1969 by researchers at IBM. Edgar R. Cord was the lead researcher. He proposed 12 rules of what makes the database management system a true relational system. We won't go over each rule, but I want to focus here on Rule 1 because it's particularly important for this lecture. Rule 1. The information rule. It states that all information in a relational database is represented explicitly at the logical level in exactly one way by values and tables. Rule 1 is what we are trying to achieve with data modeling. Remember, this is all abstract concepts of relational modeling and what makes a system a valid relational model. So why is the relational model important? Number 1, standardization of the data model. It takes work and effort to get your data transformed into rows and columns format. But once you do this, your data is standardized and we'll be able to query it with SQL. Number 2, flexibility in adding and altering tables. Relational database gives us the flexibility to add tables, alter tables, and add or remove data. Remember, these are the basics of what makes a database also a relational model. Then we have the data integrity. Data integrity is the backbone of using a relational model. Strong data typing ensures data that does not fit the model will not be inserted, causing corruption. Number 4, SQL. SQL is a standard language that can be used to access the data with a predefined language. Then we have simplicity. And then finally, we have intuitive organization. The most important benefit for us is to remember that data is systematically stored and modeled, and that the modeling process is an intuitive process. If you have created a spreadsheet in Excel, you have created tables and modeled your data. It was so natural, you didn't even have to think about that you were doing data modeling, but you really were. More complicated systems require more intense thought and experimentation, but the basics are really the same. Now let's quickly see the difference between online analytical processing or OLAP and OLTP, that's online transaction processing. So in OLAP, database optimization for these workloads allow for complex analytics and ad hoc queries. These types of databases are optimized for read. Now let's see OLTP databases. So these databases are optimized for workloads that allow for less complex queries in large volumes. The types of queries for these databases are read, insert, update, and delete. So let's go through an example so that we can understand the difference between these two types of databases. OLAP query will tell you how many shoes last week were sold in stores in California. You can see that it's already an aggregation that you would have to do to get the data. You are doing analytics and aggregations on your data. So those are OLAP queries. An OLTP query will tell you the price of the shoes. Imagine just doing a select star on a particular table and getting back a result. OLTP queries will have little aggregations, really if any, while OLAP will heavily focus on aggregations. So here are two questions for you. Question 1. True or false? OLTP queries are read heavy and focus primarily on analytics. The solution is false. Question 2. What makes data modeling for relational databases different? Options are the ability to model data in a way that's intuitive. The second option is you must model for your queries first. The third option is there is no flexibility or agile nature to this process. And the solution is the ability to model data in a way that's intuitive. So now let's talk about structuring the database. So two biggest concepts of data modeling and relational databases are normalization and denormalization. And we looked at them briefly in the previous lecture. So we use normalization to reduce data redundancy and increase data integrity. Reduce data redundancy, right? So what does data redundancy stand for? It means copies of my data. And increase data integrity. What does data integrity mean again? It means that the answer that I get from the database is the correct answer. So those two are very important things. Now in denormalization, it's a process that must be done if you're doing read heavy workloads to increase the performance. So normalization will feel like a natural process. But from the third normal form, it starts to feel a little bit unnatural, but that's okay. But overall, it does feel like a natural process. You're going to be reducing the number of copies of data and increasing the likelihood that your data is correct in all locations. And that feels very natural and feels like something that we want to do. On the other hand, denormalization will not feel as natural. You're going to have duplicate copies of your data, and that may not feel natural to you, right? That may seem like, well, if I have all this information in one column, I don't want to have it at all in another column in a table. I want to normalize it. But sometimes denormalization must be done for performance reasons, and we are going to talk more about that in a couple of minutes. So these tables are going to be more focused on the queries that will be run. This is what we were talking about when we were talking about NoSQL databases in the previous lecture. So let's focus a little bit more on normalization. The process of structuring a relational database in accordance with a series of normal forms in order to reduce data redundancy and increase data integrity is called normalization. So this process was actually proposed again by Edgar Cord. He must sound like he must be the father of relational databases, right? Normalization organizes the columns and tables in a database to ensure that their dependencies are properly enforced by the database integrity constraints. We don't want or need extra copies of our data. That is data redundancy. We want to be able to update our data in one place and have that be the source of truth. That is data integrity. The more copies of the data, the more likely that our data could be out of date or not updated or be incorrect. Let's take a look at an example. So here we have an example of the table that we'll be using for the demo in our exercises. Let's say that we have a table called music library. It looks pretty standard. We have some 2 rows here and a variety of columns. But this is not a normalized table. As we walk through the process of moving to the third normal form, we will learn why. So let's see the objectives of normal form. To free the database from unwanted insertions, updates, and deletion dependencies. It's pretty simple. This is one of the primary objectives of normal form. If I want to update my data, do I want to do this in one place or many places? Ideally, I want to go and update that data in just one place. That seems natural, right? It seems it makes logical sense. Number 2, to reduce the need for refactoring the database as new types of data are introduced. When a new piece of information is added, for example, our company is now collecting email addresses for our customers, we don't want to have to completely change our data model and collection of tables. We should either be able to simply add a column or a new table with a foreign key, especially if we have normalized tables. We want to make sure that we can just add a new table with a foreign key. We don't want to have to go through and read each row and edit each row. Also think about the applications using your database. If you make human exchanges, it may affect those applications. Number 3, to make the relational model more informative to users. The relational model should be very intuitive and it should make sense to others, just like good code. These models should model real-life concepts. Number 4, to make the database neutral to the query statistics. Try not to design your tables for particular queries. Try to make sure every and all new information and insights can be gathered from the tables over time. So please note, this is the exact opposite of what we discussed about NoSQL tables and what we talked about Apache Cassandra and modeling our tables to our queries. This is the exact opposite of that. The process of normalization is a step-by-step process. First normal form, second normal form, and third normal form. This is a progressive process and each form must be met before the next form can be completed. There are more normal forms, actually up to 6 normal form, but most relational databases strive to achieve and most data modeling designs strive to achieve a third normal form. Fourth or sixth normal form is really just for more academic and research purposes, and it's not really done in production. Now let's go over each one of these normal forms one by one. So first, we have the first normal form. So how to reach for our first normal form? So you want to make sure that you have atomic values. Each cell should contain unique and single values. So that means no sets, no collections, or no list of values in a column. Next, we should be able to add data without altering tables. But what this really means is by adding or removing columns. Sometimes this has to be done. Sometimes you just have to add a column to your table to just make it make more sense, or sometimes you need to remove a column from your table even if it makes sense. So you need to be able to alter the table, and that's fine. Next, separate different relations into different tables. So for example, let's talk about these two tables that we have in this example. We have a customer table and a sales table. We could probably combine these tables into just one table, but instead we want to have logical groupings like customer and sales. We don't want just one giant table that holds all the information possibly we can get. That's not what we want to do here, right? So we want to keep the relationships between tables together with foreign keys. We need a way to keep the relationships at the table that have been separated. They are not all in one big table. They are in separate tables now. So we need to make sure that we can still link them together by a key. This will need to be unique. So again, let's take a look over here at our customer and sales table. So here we have columns such as name, email, ID and city. And over here in the sales table, looks like maybe we are selling something. We have customers and we have sales. Looks like our customer and we have the names over here, and maybe they spent some amount on an item on a transaction. So it's easy for us to see that we could have this transaction column in the customer table, right? But it doesn't really belong there. It's not really information about our customer. And thus we have separated it out into two tables to get to the normal form. So from there we are able to join these tables by this key here, which is name. Now this is just an example and we probably don't want to use name as our key because it's not unique. But in this case, for our little example, it sounds fine. So now we can say that our table is in first normal form. Now let's move on to second normal form. How to reach the second normal form? Well, the very first thing that you have to do to start getting your information in your data model into a second normal form is to be in first normal form. You have to do that before you can progress on a second normal form. Again, it's a progression. Then all columns in the table must rely on the primary key. Let's stop and think about that for a minute. It means that there should be no composite keys to get fields. I shouldn't need two elements to get a third. If the column does not help describe the primary key, such as just customer sales employees, that it may not fit in the table. Also, if the column depends on multiple columns, it may need its own table. So let's take a look at the example here. Here we have, and this is our first table, we have store-wide customer ID, customer name and email. So in this case, we are going to need both the store ID and the customer ID to get our customer. Our store ID is not unique. So we need two keys to get our customer. And we need that so that our table could be in second normal form. But we don't want to do that. So what we can do is break that up into two tables. One, store ID and customer ID, and our customer table that will have customer ID and then the rest of the information about our customers. And then from there we can easily join these tables on customer ID to get more information. So that brings our table in second normal form. Now let's move on to third normal form. Now remember, first we must be in the second normal form. Remember, this is a process and it's an iterative process. First, you start with a non-normalized table, then first normal form, then second normal form, and now finally the third normal form. But we must be in the second normal form. From there, we must not have any transitive dependencies. Let's take a look at an example here. In this case, we have an awards table of music awards. So in this case, we have a row with our music awards. We have the Grammys, CMA and the VMAs. And then we have the years. Right? Because both of these music awards happen every year. So we need to have both the music award and the year to be able to know who is winning the record of the year. And in this case, so the Grammys in 1965, we are going to get the Beatles. And then from there, we have the lead singer of that band. Now, this transitive property, the fact that you need both music awards and the year to get to the winning record of the year, and the fact that now you have this extra amount of data here for the lead singer, and as you can see, both in 1970 and 65, the winners were the same. Both the Beatles and the lead singer is now duplicated here. The fact that we need to have this transitive property to get the lead singer makes it not in third normal form. So from there, what we want to do is break up the table into two tables. We don't want to have duplicate data in the lead singer. We do not want to have duplicate data as we may have data integrity issues with updating the lead singer. we wouldn't want to do an update on this row and not on this row. So if we separate that out, we can easily avoid that problem from here. We'll have our awards table and we'll have our music award here and the winner, and then we'll have another table called lead singer, the band name and the lead singer here. So from here, if we do an update, we only have to do it in one place and we are able to get our original information back by joining on winner record of year and band name. So let's review normalization and the three normal forms. We saw that normalization is a series of rules that your database's table structure must pass in order to be considered a good relational design. The individual rules are called normal forms, and they must be tested in order, like passing through a series of gates or checkpoints. In other words, you can't satisfy the requirements of second normal form without first satisfying the requirements of the first normal form. It's generally accepted that a relational database that meets the requirements of the third normal form is in pretty good shape, so we only need to look at the first three normal forms. We started with the first normal form. We said that tables that satisfy 1NF will have columns that only store a single piece of data. You'll know when a table is in violation of the first normal form when you see something like the person column is storing a comma separated list of values. The solution is to try and break it out into more columns, but in that case, we would just wind up with multiples of the same kind of column like person 1, person 2 and person 3. So we have to resort to numbering them, and this isn't a great solution. So the best solution is to move the person into their own table and create a relationship back to the original records using a picture number. Another common way that the first normal form is violated is storing addresses, which is just a comma separated list of values in disguise. If you store an entire address in a single column, it makes the data hard to work with. Instead, we create a separate street address, city, state, and postal code columns in the table and separate out each discrete component of the address. Now let's review the second normal form. Now this one might be relatively easy to pass depending on how you set up your primary keys. If all your tables use only a single field or column as their primary key, then congratulations, you've already passed the requirements for 2NF. If you are using a composite primary key, that is to say, a primary key that requires two or more fields in conjunction to uniquely identify a record, then we have a little bit of work to do here. A table is in second normal form if all the fields in the primary key are required to determine the other non-key fields. Here's an example. In our pictures database, the people table had a concatenated key that combined the picture number and the person's name to uniquely identify each record. This created a table that would not allow two records for the same person in the same photo. It's also a setup that unfortunately creates a situation where we can't have two friends with the same name in the same photo. But I am going to go ahead and ignore that problem for just a moment. Let's say that we want to store the last names of each person, so we logically add another column to the table. Now this table violates the second normal form because the last name can be entirely figured out just by the person's first name. In other words, you don't need both columns that make up a composite primary key to determine the last name. The picture number is irrelevant. We can fix this and bring the table back into compliance with second normal form by splitting the data into another table and joining them together with a one-to-many relationship. We can also take the opportunity here to create a better, more unique primary key for the person table, so that we can now have two people with the same name in the same photo. Now that brings us to the third normal form. The third normal form follows a similar pattern to the second normal form, but instead of checking against the individual components of a composite primary key, we'll check each non-key column against every other non-key column. Here we are looking for columns that are functionally dependent on another piece of information that isn't the primary key. Here is an example that violates the third normal form. We've decided to add information about where each person lives, and for the flexibility in how we use the data, we want both the two-letter state abbreviation as well as the full name of the state. Third normal form is only concerned with non-key columns, so we can ignore the person column for now. Now evaluate every other column to see if you can definitely figure out the value of one column from the value stored in another. You might think that first and last names fit that description, and maybe for this limited number of records it does. But it is certainly possible that the table could contain two people with the same first name but different last names. So that's not a functional dependency. We do have a functional dependency between the two state columns. Since abbreviations are unique, anytime we see WA, we know that it means Washington. It doesn't matter how many records this table has, that will always be the case. Violations of third normal form often occur when two fields are simply stating the same thing in a different way. Since state abbreviation is entirely dependent on state or vice versa, one of those two column fields should be removed from the table and, you guessed it, put into a related table. Compliance with third normal form is typically considered a great place to get for many business database systems. There are additional normal forms beyond 3NF, but they are increasing obscurity and complexity. For many, getting to 3NF will solve most of the problems that can cause issues with the database performance. So here's the question for you. What is the maximum normal form that should be attempted while doing practical data modeling? Is it first normal form, second normal form, third normal form, or fourth normal form? So the solution is, of course, third normal form. Alright, so now we are going to walk through the actual process of normal forms, of taking a data that is not in the normal form and walking all the way through getting it to third normal form. So again, as you can see, we are back in our Jupyter notebooks, and I have opened the notebook for creating normalized tables. So in this demo, we are going to walk through the basics of data modeling in normalized form. We will create a table in PostGRE SQL, insert rows of data, and then do a simple join to show that these tables can all work together. Because remember that when you are getting tables into normal form, you are always going to need to combine those tables. Just by separating them, it doesn't mean that our data isn't related. It's very tightly related. So you need to make sure and get all information from that data with the joins. Again, the ability to do joins is a benefit of using a relational database. Alright, so let's come to cell 1. Here we are going to import our library that we are going to use, and that's the Python driver psychopg2. Now let's come to cell 2. Here we are going to connect to our database and we are going to get our cursor, and then we are also going to set the auto commit is equal to true. Okay, so that's done. Now we saw this table earlier in the lecture also, but let's just walk through it. So imagine that we have a table called music library. So the table name is music library and we have 5 columns here: album ID, album name, artist name, year, and list of songs. So let's go through the first row over here. Our album ID is 1, our album name is Rubber Soul, and the artist name of course was The Beatles, and the year it was released in 1965, and here we have some list of the songs that were in the album, like we have Michelle, Think for Yourself, and In My Life. So now let's just translate this table into a simple create table statement and insert our data. So in cell 3, I am going to create a table if it does not exist, and I am going to model exactly what I saw here in my diagram. So we have music library, and then we have an album ID, and that will be int. Then we have album name, and that will be varchar. And then we have an year, which will be int, and we have songs, which will be a list of text. And I am going to put my create table statement in try and except, and this is done to catch any errors. Then I am going to do simple inserts, and we are going to insert the data into the database. So here's our insert statement, and we insert into our music library, and then we have our column names here. So those are album ID, album name, artist name, year, and then songs. And so note that we are going to insert 2 rows of data here, and then we are also going to put them in try and except to just catch any error if there are. And then finally, we are going to do a select star from music library to make sure that our data actually got inserted and it looks the way we thought. Then from there, the code just loops through and it prints that onto the screen. And remember, again in Postgres, feel free to do a select star. There are no performance issues like they were in Apache Cassandra. So now let's come to cell 4, and we are going to think about moving to our first normal form. Again, this data has not been normalized. To get this data into the first normal form, we need to remove any collections. So as you can see, we have list of data over here. We need to break up the list of songs into individual rows. So in this case, we are going to make a new table called Music Library 2. We are going to have album ID, album name, artist name, year, and song name. Because we are not going to have a list, we are going to have songs, and that's why we have song name column over here. So let's just go through the first row of data. Again, we have album ID, which is 1. We have the album name, which is Rubber Soul. The artist name is The Beatles. The year it was released in is 1965, and the song name is Michelle. So again, we are going to translate our data into the create table statement like before, and I'm not going to walk through this because it's just the same, and we are going to insert into our table and store the data. So remember that our table name here is Music Library 2, and then we are going to insert all our values. And this might look a lot of code to you, but don't be alarmed by it. It's all just entering data. And these are simple insert statements. So now let's come to the end of this cell, and what we are going to do here is a select star from Music Library 2, and we are doing this to make sure that our data was entered properly. So now once we execute this cell, it looks like this was successful and our data looks correct. So now let's come to cell 5 and let's start thinking about moving to the second normal form. So that was easy enough, right? We just broke up our collections to get it into the first normal form. Now let's move to the second normal form. We have moved our data to the first normal form, which is the first step, and that's the prerequisite to even start thinking about the second normal form. But our table is not yet there in the second normal form. So while each of the records in our table are unique, right? Let's go back and look at the table representation here. So we can see here that each one of these rows is unique, except there are many elements that are duplicated. So let's keep that in mind. So now let's scroll back down here. So our primary key in this case, the album ID, is not unique. We had many duplicates and we had many different columns. So we need to break this into two tables. So let's break it up into album library and song library. So here we are going to have a table called album library with album ID, album name, artist name and year. And then we are going to have a song library with a song ID, song name and album ID. So now in this case you already see that we have reduced the number of duplicates. So you can see here that the number of duplicates on album ID have been reduced. Now we just have two rows here in this table, and this is called album library. And then we have our song library, to which now we have added a song ID column, and then the corresponding album ID, and this will join with this table to get the rest of the information here. And then we have our song name. So now let's come to cell 5, and here we are going to create those tables and insert that data. Again, this looks like a lot of code, but it must be pretty straightforward by now. So from here, we are going to do a select star on that table. And we just want to do this to make sure that the data was inserted into our tables correctly. So we have just printed it out to make sure that the information is showing correctly. So as you can see here, the information is printed out correctly. So now let's come to cell 6. Let's do something that we haven't done in the past. So let's do a join here so that we can get the information that we had in our first table. Because let's say I wanted to do a query that gets back my album name, album ID and artist name. So we want all of them at one time. So what we need to do is we need to do a join. So in this case, we are going to do select star from album library and then we are going to join it on the song library table. So we are going to join these two tables and we need to join on a common column. So that will be album ID. So now as you can see here, in this case, we have got back the same information that we had before. So we now have our album ID, our album name, artist name, year and song ID. In this case, I did not remove the other columns. It just joined both of the tables as is and then it's printing the album ID and then the song. The important thing here is that how we moved from first normal form and then to second normal form. So that's the key over here. Now let's move on to the third normal form. Let's check our table for any transitive dependencies. So album library can now move artist name into its own table called the artist, which will leave us with 3 tables. So we are going to make album library 2 and this is going to have album ID, album name, artist ID and year. And then we are going to have a song library which will have song ID, song name and album ID. And then we are also going to have an artist library and this will contain the artist ID and artist name. So you can see the representation of our tables over here. So that's our song table, that's our album table and that's our artist table. So now let's come to cell 7 and again we are going to create those tables and then we are going to print them out to see what data has been inserted. Then from there we come to cell 8 and here we are going to do 2 joins on those 3 tables. So if we do this, that is 2 joins on 3 tables, again we'll get back all the information that we originally had in our first table. So when we run this cell, we get the output that we wanted and that looks great. It's all the information that we had in our first table. So we are all done and we have normalized our dataset. We have gone all the way through a denormalized table to a normalized table, reducing duplicates all along the way. So this demo was all about getting that data integrity and reducing the data redundancy. And just for the sake of this demo, in cell 9, I will drop all the tables that we had created. So as you can see, we had a lot of them. And finally, we are going to close our connection. We are going to close our cursor and this will be the end of this notebook. So we saw in this notebook that we were successfully able to maintain the data integrity and reduce the data redundancy. And this concludes our demonstration. So now we are going to talk about denormalization. We just spent a lot of time focusing on normalization. So now it's time to move on to denormalization. Again, this is really one of the most important concepts. So denormalization is the process of trying to improve the read performance of a database at the expense of losing some write performance by adding redundant copies of the data. So the process of denormalization is all about performance. Joins on the database allow for outstanding flexibility, but they are extremely slow. So we saw that in the last demo that we were able to get all the way there to third normal form, but then we were able to get the information that we originally had in the first table by doing joins. At one point, we were able to get everything with 2 different joins on 3 tables. So that's incredibly flexible and it's really fantastic that we have that. But the joins are very slow. So if you are dealing with heavy reads on your database, you might want to think about denormalizing your table. Denormalization comes after normalization. So this is again all about a process. You get your table to normalize form and from there you denormalize it. Denormalization may also require more space on your system and there's going to be more copies of the data. While this shouldn't be ignored, it has become less of a concern as space has become less expensive and it's not really a limiting factor. When we do denormalization, we want to do a logical design change. That means that we are going to model our data differently so that we have denormalized tables. So the designer is in charge of keeping the data consistent. The reads will be fast, the select statement, but the writes will be slower, which is the insert, update and delete statement. We've talked a lot about getting our data consistent, but what does this really mean when especially dealing with denormalization? So once you add more copies of your data, that means that you'll need to make sure that each one of those copies is updated or deleted at the same time. For example, if we have two tables with a column address of customer, then you will need to do two insert statements when adding my address. Or if you are updating the address, you will need to change those in two places. Well, this is not difficult in theory or on small projects. But this gets very complicated when you're talking about large data sets with many applications using the data. It's just something that we need to be aware of and make sure that we are handling it if we want to use denormalization. So let's talk about an example over here with two tables. So here we have a table called customer and a table called shipping. Now remember, denormalization is all about performance. Let's say we are getting heavy reads from both of these tables, trying to get information about how much our customer spent and the kinds of items that we need to ship to their house. Maybe something that they've purchased. Now, we could have these all in different tables split up and then we would use a lot of joins to aggregate all that data together. Or we could just separate it out and have two tables with duplicate sets of information, right? And both tables have the city column, and that's okay. Duplicate data is okay in denormalized form. From there, we'll have information that's specific to that concept, like shipping. So I'm going to ship a particular item to my customer for which he spent a particular amount. So in this demo, we are going to walk through the basics of data modeling from normalized form to denormalized form. Again, remember these examples are simple, but imagine the situation at scale with large databases with many users and the need for quick response time. So again, we are doing denormalization because it's all about the performance. So again in cell 1, we are going to import our library, and then in cell 2, I am going to connect to my database the same way we have done in past. So let's get started, and let's start with our normalized and third normal data form. Okay, so let's get started and let's start with our third normal form dataset. So here we have a set of tables that we had in the last demo, but now we've added a new table called song length. Again, we have the same columns and these are the same columns that we had in our third normal form. But now we've added this new table song length. So we are going to have one column for song ID and the other column for song length in seconds. So here are our tables. So here's our song ID and there's the song length in seconds. So this is all in third normal form. So coming to cell 3, we are just going to create those tables and do the inserts over here. So nothing fancy here. And again, it's a lot of code. It may look a bit overwhelming, but it's really not. It's just really going through creating the table and then writing the insert statements. Then in the next cell, in cell 4, we are actually going to print the results. So we have to make sure that everything got inserted into the table correctly. So when we print the results, here we have our album library, and that has 2 rows of data. And then we have our song library, which has all our songs. Then we have the artist library. This one has only one result. And we have our song length, and we have results for that. So now let's come to cell 5. Let's say we want to do a query that gives us all of these columns, that are artist ID, artist name, album ID, album name, year, song ID, song name, song length. So we want everything. So in this case, we are going to have to perform a 3-way join on the 4 tables that we have created. We can do that, and it is possible. Let's just take a look at the join over here. So in cell 5, we are going to select all of these columns, and then we are going to do a join. So first we are going to do a join on artist library and album library, and we are going to join the tables on artist ID. Then we are going to join that on album ID from the album library and song library. And after those tables are joined together, we are going to join them with another table, that is song length table. And we are going to utilize the column of song ID on both the song library and song length. So as we can see here, it's a pretty complicated query. So once we run this cell, we see that it worked. We got all the information that we wanted. We were able to get all the data we wanted, but we had to do a 3-way join to get there. Now while it's great that we have that flexibility, we have to remember that joins are slow. And if we have a heavy workload and that requires a low latency queries, we want to reduce the number of joins. While it's great that we have that flexibility, we have to remember that joins are slow. And if we really have a heavy workload that requires low latency queries, we want to reduce the number of joins. So let's start thinking about denormalizing our normalized tables. So with denormalization, we want to think about the queries that we are running and how we can reduce the number of joins, even if that means duplicating the data. So let's just go through an example here. So we have some queries that we might want to run. So in this example, let's say query 1, I want to list all of my songs. So that's what I want. I want to do a select, and I want the artist name, album name, year, song name and song length. So that's the columns that I want to see. And I want these from a minimum number of tables. I don't want to do a ton of joins. Now for my second query, I want to know the length of each album in seconds. So here I am going to do a select album name, and then probably I want to do a sum and aggregation on my song length. And then from there I want to use minimum number of tables. So then I will have to do a group by album. So let's look at our first query in detail. So again, as we have discussed the query and we want to select artist name, album name, year, song name and song length from a minimum number of tables. To reduce the number of tables, let's first add song length to the song library table and artist name to the album library. So from here we are going to create a table called album library, and that will have the columns album ID, album name, artist name and year. And then we are going to create a song library table, and that will have song ID, album ID, song name and song length. So this is what the tables look like. So now let's come to cell 6, and we are actually going to go through the process of creating those tables. So we will call these tables album library 1 and song library 1. So we are going to do create table statements, and then we'll do the insert statements. So that's what we are going to do in this cell here, and again it's a lot of code, but it's pretty straightforward in what it's doing. So once we are able to insert all of the rows, we see that there were no errors thrown. So now let's come to cell 7. Now we can do a pretty simplified query to get all the information we need. We are only going to do one join because we have two tables with our information. So what we can do is, we will do a select artist name, album name, year, song name, song length from song library 1, and we are going to join that with album library 1 on album ID, and that's the foreign key. So we are going to join on that column. Now once we execute that, we get back all the information that we wanted. So in the results, we see that we have some duplicates, but that's okay. That's part of denormalization. Now in cell 8, let's say we want to run this query. So we select album name, song length from a minimum number of tables and do a group by album name. So basically what it's saying, I want to know how long each one of my album is. So we should be able to do a join on these tables that we created. But what if we don't want to do a join at all? Maybe this is something I need to be able to return to my users of my database very quickly. So I don't want to have to do a join here. So why don't we just create a new table with the information we need? So let's create a table called album length. And then we have the columns song ID, album ID and song length. I don't need any other information. I just need the album name. So in this case, I'm going to create a table called album length, and we will have song ID as int, album name as varchar and song length as int. So that's all I need in my query over here. And then we are going to create it. And yes, it's going to have some duplicate data, but that's fine. So now let's just create the table here and we will do our inserts over here. And now we will come to cell 9. So now we are able to do the query. We can do a simple select album name, sum on song length from album length, group by album name. So as you can see here that we did no joins and this executed pretty quickly. So that's great performance. So here's my album name Rubber Soul and it's 445 seconds long. And then we have our album Let It Be and it's 467 seconds long. So we have successfully taken a normalized set of tables and denormalized them in order to speed up our performance and allow for simpler queries to be executed. So then again, for the sake of this demo, I will drop all my tables and then finally we are going to close our cursor and we are going to close our connection. Now let's see the data definition and constraints. The create statement in SQL has a few important constraints that are highlighted below. First, we have the not null constraint. The not null constraint indicates that the column cannot have a null value. You can see the syntax for adding a not null constraint to the create statement here in this slide. You can add not null constraints to more than one column. Usually, this occurs when you have a composite key, which will be discussed further. Now next, we come to the unique constraint. This constraint is used to specify that the data across all the rows in one column are unique within the table. The unique constraint can also be used for multiple columns, so that the combination of the values across those columns will be unique within the table. In this latter case, the values within one column do not need to be unique. You can look at the example and the syntax of the unique constraint in the slide. Next, we come to the primary key constraint. Now the primary key constraint is defined on a single column and every table should contain a primary key. The values in this column uniquely identify the rows in the table. If a group of columns are defined as a primary key, they are called a composite key. That means the combination of values in these columns will uniquely identify the rows in the table. By default, the primary key constraint has the unique and not null constraint built into it. You can see the example and the syntax of primary key given in this slide. Now let's see what is upsert. In RDBMS language, the term upsert refers to the idea of inserting a new row in an existing table or updating the row if it already exists in the table. The action of updating or inserting the row has been described as an upsert. The way this is handled in PostgreSQL is by using the insert statement in combination with the onConflict clause. The insert statement adds in new rows within the table. The values associated with the specific target columns can be added in any order. You can see the example of the insert statement in the slide. So we can see that we have inserted a new row of data in our customer address table. Now let's assume that our customer moved and we need to update the customer's address. However, we do not want to add a new customer ID. In other words, if there is any conflict on the customer ID, we do not want that to change. This would be a good candidate for the onConflict do nothing clause. So as you can see, we have added the onConflict do nothing clause on the customer ID. Now let's imagine that we want to add more details into the existing address for an existing customer. This would be a good candidate for using the onConflict do update clause. So as you can see, we have done an onConflict on the customer ID, and so if there will be a conflict, we update the customer street and we have written excluded.customer_street. So that's the way we handle onConflict do update clause. In order to get most out of our Postgres, we need to have a good understanding of how relational databases are structured. The foundation of any database is a data table. Data tables are used to organize and store information that you want to keep track of. As we saw in our first explorations of Postgres, you can create a data table by defining the different columns that it's composed of. In database terminology, these columns are called attributes or fields, and they are used to store individual descriptive components of each item that's stored in the table. For instance, in a table about books, you might have a column for the title, author, and publication year. Note the naming conventions that I am using here. In Postgres databases, it's standard to use all lowercase letters for all tables and column names, and to separate multiple words with an underscore character. It's not strictly required to do this, but it's the format that almost every Postgres developer follows. So it's best to stick with the general practice when developing your own databases. Once you have created your tables, you can start adding rows of data. Each row of the table will represent a single item. If you think of the columns as descriptive adjectives, then each row are the nouns, the people, places, things, or events that you're storing information about. In this case, each row is an individual book. Each additional row in the table is information about another book. When it comes to read data back out of the table, it will be very important that we can uniquely identify each row in the table. In this table about books, you can simply ask for the book by its title. But if I were to ask you for a book published in 1847, you won't be able to precisely identify which single book I meant. As we add data to this table, it would be pretty common to have multiple books by the same author. Eventually, this table might even grow large enough to actually have two books with the same title. So we can't really rely on the title to always uniquely identify a row in this table. For this reason, we need to add one additional column to this table's design. The standard convention for this column is to name it with the name of the table followed by ID. This will store a unique identifier for each row in the table. So if I were to ask for book ID number 3, then that will always point to the specific edition of Wuthering Heights by Emily Bronte, published in 1847. The book ID column is called the table's primary key. A table's primary key column always has a unique constraint applied to it. Its only job is to make sure that every row in the table always has at least one piece of information that's different from all other rows. Usually, this column doesn't have any real world significance. The fact that the time machine was book ID number 1 and Jane Eyre was book ID 2 doesn't have any meaning outside of this database. It's not a ranking and it doesn't imply any sequence. Or give you a count of how many items in the table, or have any other significance other than to say that book 1 is a different thing from book 2. So that's all a primary key does. If you think about your own life, you will find that primary keys can be found all over. Your credit card number, for example. It's a primary key in your bank's database that uniquely identifies your card from every other card in the world. Your library card, social security number, phone number, email address, all of these are primary keys in someone's databases. And all of those point to you as a unique individual. So that's the structure of a database table. Each column holds a single attribute about the items in the table, and each row represents an individual item. The primary key field is added to ensure that every row can be uniquely identified as a separate entity from every other row in the table. When we created our first table in Postgres, you might remember that we had to name each column and pick a data type for the information that each column will hold. Let's discuss the role that data types play and the design of your table. If we take a look at the books table again, you will notice that each column is storing the same kind of information all the way down. The book ID is always an integer. It's never a text, it's never a fraction, it's always going to be a whole number. The book title will always be text, as will the author column, and the publication year will always be an integer, just like the book ID. Because we know that with certainty what kind of information will be stored in each column, and that becomes an important component in the design of this table. Postgres supports a variety of data types that you can use to control what kinds of information can be stored in each column of your table. We can group them into categories such as numeric values, character or text values, date and times, monetary amounts, binary data types for storing files, the Boolean type for simple yes or no or true or false information, and geometric types for points, lines, polygons, and other shapes that you might use for creating maps. There are many other data types that Postgres supports out of the box, but I want to focus on the three most common: numeric, character, and date time. The numeric types are used for storing numbers. When you only need whole numbers with no fractional component, you can choose between integer, small int, or big int, depending on the range of values that you need to store. The integer data type will allow you to store numbers between approximately -2 billion up to +2 billion, and it should be the default choice for when you need to store integer values. If you try and store a value that's outside of the accepted range, Postgres will return an error. When your numbers include fractions, you will need to use either numeric or decimal type. Both of these are identical and allow the database designer to specify exactly how many digits before and after the decimal point the column will allow by specifying a precision and a scale for the number. For instance, the number 123.45 includes 5 total digits, with 2 of those to the right of the decimal point. This would require a numeric data type with a precision of 5 and a scale of 2, or a numeric 5-2 data type. And finally, there are two data types for storing float point values that are commonly used in data science applications to manage extremely large and extremely small numbers. When your table columns need to store a character data, you have a number of options here as well. When all the values in the column will be of the same length, you can use the character or the char data type. Inside of the parenthesis, you will specify the number of characters that the column will hold. This is a great thing for things like 2-letter state abbreviations or a 16-digit credit card number. Anything that you know will always be of the same length is a good candidate for the character or char data types. When you need to store text that doesn't have a fixed number of characters, then you'll want to use the character varying or the varchar data type. This will be the best choice for storing our book titles and author names. Here, the number in parenthesis indicates maximum number of characters that the column can hold. Often, picking a suitable number of characters will be a guessing game. You want it large enough to hold every value that you're likely to ever put in your column, but not so large that it's ridiculous. At the time of recording this, the Guinness Book of World Record says that the book with the longest title includes just over 26,000 characters. So if you really want to store that book in our database, you'll need a varchar 26021 to hold it all. And when you want to store text of unlimited length, you need to use the text data type. Text is perfect for things like blog posts and newspaper articles. Finally, let's take a look at the date and time data types. These are pretty straightforward. The date data type will store dates accurate to the day for any date between 4713 BC and the year 5 million AD. So we have a bit of time before we run out of dates that you can store in a Postgres database. The time data type will store the time of day and is accurate to 1 microsecond. The timestamp data type will allow you to store both time and date in a single column. And finally, the timestamp with time zone data type adds time zone awareness to the dates so you can perform more accurate comparisons of dates and times from around the world. So those were the most common data types that you will use for storing numeric, character, or a date and time values in your Postgres databases. So PostgreSQL is a relational database management system, and that word relational is an important description. It's what makes a Postgres database more than just a collection of spreadsheets. In order to understand how table relationships work, let's take a look at our books table again. Let's suppose that you want to keep the track of the birth and death dates of each author. You might try and add two columns to the books table to store this information. The problem with that is that the author birth and death dates don't really describe the topic of this table. They just describe the authors. Worse, if you add another book by the same author, for instance, H.G. Wells also wrote War of the Worlds, the author birth and death dates would get repeated in our database. And this would be a wasteful duplication of data, and it will create a situation where the data could become inconsistent. For instance, if each of these books by H.G. Wells listed different author birth and death dates, you won't know which ones to trust. So it's not a good idea to store these pieces of information in the books table. The solution is to create another table that's just about the authors. We'll need the author name and their birth and their death dates, as well as another primary key for this table to make sure that we can keep each author separate from every other author. Now I can find out who wrote that book as well as the time they were alive. There's one more piece to this problem though. Remember back when we talked about the primary keys in this books table? I mentioned that it might be possible for two different authors to have the same name. Well, that still applies here. So when I look up the birth date of the author of Time Machine, I want to make sure that I have the right H.G. Wells. So instead of storing the author's name in the books table, it would make sense to refer to the primary key from the author's table instead of the name. I'll make that change to the books table, and you will see that it makes no difference on our ability to figure out who wrote that book. Now it says that The Time Machine was written by author 101. I take that piece of information to the authors table to find the name, birth, and death dates. What we have just done is created a relationship between these two tables. The author ID in the authors table is a primary key for that table. The author ID in the books table refers to the authors table for additional information about each book. In the books table, the author ID column is called a foreign key, and that's the basic arrangement of what makes a relational database. Multiple tables separate information out by topic, but would allow information to be cross-referenced by following a thread between matching values in the primary and foreign key columns. This design allows Postgres database to efficiently store data with a minimum of redundancy while protecting against inconsistencies that can make a dataset untrustworthy. Alright, so now we are moving on to a new topic. We are leaving the denormalization and normalization. So we are going to talk about fact and dimension tables. So these work together to create an organized data model. While fact and dimension tables are not created differently in the DDL, they are conceptual and extremely important for organization. So again, these are different tables you create in the sense that you are going to do a different create table statement, but they are different in the fact of how we are conceptually understanding our data model. So again, fact and dimension tables work together to solve business problems. You will find at least one or more fact tables for each dimension table. They are created in the same way as a conceptual concept of data modeling. Fact and dimension table concepts will help us to understand star and snowflake schemas, and we'll get into that in the next couple of slides. Fact tables consist of measurements, metrics, or facts in a business process. Fact tables are made up of facts, events that have actually happened. Think of a customer transaction and how much they spent. That transaction ID might be used as a key in the dimension table to tell us more about the customers and the individual items bought. Fact tables can be used as aggregations of data, but are not meant to be updated in place like a dimension table would. Fact tables normally have ints or numbers, and we'll see an example coming up. Now let's move on to dimension table. A structure that categorizes facts and measures in order to enable users to answer business questions is called a dimension table. Dimensions are people, products, places, and time. Dimension tables are all the other pieces of information that are not included in the fact table. Customer information, information about products, etc. Normally, textual information or numbers that are not used for analysis like year or date. Each dimension table will have one or more fact tables joined together with a foreign key. Now let's see how we can implement the different schemas. Building off of our conceptual knowledge of fact and dimension tables, the schema that fits with this is the star schema. So, two of the most popular because of their simplicity data mart schemas for data warehouses are the star schema and snowflake schema. This is building off of our conceptual knowledge of the fact and dimension tables, and the schema that fits in with this is the star schema. The star schema is the simplest type of data mart schemas. The star schema consists of one or more fact tables referencing any number of dimension tables, and this is the most widely used schemas in the industry. So why would we use a star schema? It gets its name from the physical model representing a star shape. So a fact table is at its center and the dimension tables surround the fact table, and so they look like a star. So some of the benefits is that you denormalize your tables and it will simplify your queries. As we saw previously, getting a table into third normal form is a lot of hard work, and the join we had to do at the end of the process was very complex, and we were working on a very simple dataset. Star schema allows for the relaxation of these rules and makes each queries easier with simpler joins. So these are the benefits of using a star schema. There may be some issues that come up with denormalization. The issue that can come up with denormalization will happen when you are using a star schema. Issues around data integrity and decrease in query flexibility will come up. Data integrity is an issue that may come up again because you're denormalizing your table and because you will have duplicated data spread across multiple tables. So this might cause a data integrity issue. And then decrease in query flexibility. Again, when you denormalize your tables, you model to your query and you're not able to do as many ad hoc queries on your table. Also, the drawback is in many-to-many relationships. This has been simplified to one-to-one mapping, and that is all that star schema supports. Many-to-many relationships are hard to support and are just an abstracted way for the sake of simplicity and to fit the model. So here's an example that I put together that we are also going to see in our demo. So here again in the middle, we have our fact table and we are going to call it customer transactions. We are going to have a customer ID, store ID, and the amount that was spent at the store. From there, we are going to have connections again by foreign keys to the dimension tables, such as item purchased. So here we are going to join our customer ID. Here's our customer, here's the item number that they bought and the item name. So let's say that if we own a music store and we had a customer that bought an item which was an album which was Rubber Soul, and then from there the second customer bought another album. So that's one of the points of our star. So here's the other point of our star, which is customer. So now again we can join on that customer ID and we are going to get information about our customer like name, whether they were an awards member, their address and things like that. And then from there we are going to have store ID. So this now we are joining on a different foreign key. We are going to have information about that store, the city, the state, store number, address and things like that. So as you can see, we have one table in the middle and that is our fact table, and the star points are the dimension tables. So now let's talk about the Snowflake schema. This is a logical arrangement of tables in a multi-dimensional database represented by a centralized fact table which are connected to multiple dimensions. So it's a complex snowflake shape that emerges when the dimensions of a snowflake schema are elaborated, having multiple levels of relationships, and the child tables with multiple parents. So again, here we have one fact table and then the dimension table and then other dimension tables that are radiating off of that. So let's do a comparison between Snowflake versus the star schema. So the star schema is a special simplified case of the Snowflake schema. Star schema does not allow for one-to-many relationships, which is what we saw that we are able to do with Snowflake schema. The Snowflake schema is more normalized than the star schema, but it's normally in first normal form or second normal form. So now we are going to move on to the demo where we will create fact and dimension tables. So just as a note, here we are utilizing Jupyter Notebooks and Python to interact with the database. But this is just really one of the ways. This is just one way and a good way, but it's just the one way that we can represent how to connect to the database and how to create tables, inserts and do things like that. So in this demo, we are going to walk through the basics of modeling data using fact and dimension tables. We'll create both fact and dimension tables and show how this is the basic elements of the star schema. So again in cell 1, we are going to import our library. Then we are going to create our connection in cell 2. And again these are all things that we have done before. So moving on to cell 3, we are going to use that cursor to execute our queries. And then in cell 4, we are going to set our auto commit to true. So now that we have the usuals out of the way, let's imagine that we work in an online music store. There will be many tables in our database, but let's just focus on 4 of those tables, and they will be all around customer purchases. So we are going to have a table named customer transactions with a customer ID, store ID and how much they spent. From there on, we are also going to have a customer table with customer ID, name and whether they are in a rewards program or not. Then we are going to have a store table which will have a store ID and the state in which that store is located in. Then we are going to have items purchased table, and in that we will have the columns customer ID and item name. So here's an example, and we saw this. So from this representation we can already start to see that it has the makings of the star schema. We have one fact table at the center of the star and the 3-dimension tables are coming out from it. So in cell 5, let's create a fact table and insert the data into the table. So we are going to create our customer transactions table, and then we are going to insert data into that table. Now let's come to cell 6 and create our dimension tables, and we'll insert data into those tables. So again, we have here the items purchased, and then we are going to insert data into that. Then we also have our store dimension table, and we'll insert data into that. And finally, we are going to create our customer table, and we are going to insert the data into that. So now once that's done, let's move on to our queries. So here's my first query that I want to perform. So I want to find all the customers that spent more than $30, and I want to get the information about who are they, which store they bought it from, location of the store, and what they bought, and if they are a rewards member or not. So this is our first query. So in query 1, we want to find all the customers that spent more than $30, who they are, what did they buy, and if they are rewards member or not. So for this example, we want to select our name, our item name, right? Because we want to know who they are and if they were a rewards member or not. So to be able to do this, in cell 7, we are going to have to do multiple joins on our tables. So from our customer transaction table, we want to join on customer table, and so we are going to join that on the same column, which is customer ID, because that's our foreign key. So that's how we are going to combine those two tables. And from there, we want to join on the items purchased. We are going to join that on the customer transaction table that has the customer ID and the items purchased, which also has a column called customer ID. So all of this, and we want only the customers who spent more than 30. So once we execute this cell, we find that Toby is a customer who spent more than $30 on Let It Be, and he is not a rewards member. Now let's come to cell 8. So here we want to find out how much did store 1 sell. So we want to do a select on store ID because we want it from store 1, and then we want a sum on the spent column, and we want to get this information from customer transactions, and we want to group by store ID. So great, we see here that store 1 spent a total of $55.71. So in summary, what you can see here is that from this elegant schema, we were able to get facts and metrics from our fact table, which is what we did in our second query with our customer transactions. Also, information about our customers that will allow us to do more in-depth analytics to get answers to business questions by utilizing our fact and dimension tables. So again here, we were able to get a quick answer, a fact, something that's true, which is that store 1 spent $55.71. We've got that quickly from our fact table. So that here ends our notebook, and I am going to drop all my tables, and then finally I am going to close my cursor and my connection. So now we will walk through a project in which we will see how to model the data using PostgreSQL. For this project, we have a music streaming startup called SoundCloud who wants to analyze the data they've collected based on their app regarding the songs and user activity. This data currently resides in 2 directories. We have JSON files for the log data, and we also have JSON files for the song's metadata. Now our task in the project will be to model the user activity data to create a Postgres database optimized for song play analysis. We will do this by creating a database schema and an ETL pipeline. So as you can see over here, this is how the events.json file looks like. And then we have also been given the schema for the song play analysis. So we have been told that we need to create a star schema that is optimized for queries on song play analysis. So note here that we are not going to focus on the conceptual data modeling and how we come up with these tables, but rather we are going to focus on how the physical data modeling is done. So as you can see, we have the song plays table and this is a fact table. This table records the log data associated with the song plays, that is, records with page next song. And this next song page filter, it allows us to specify the user that has played a song, meaning that the user has clicked on the next song button in the app. And then we have the other fields also. We have a song play ID, start time, user ID, level, song ID, artist ID, session ID, location, and user agent. Then we also have other dimension tables called as users, which will tell us the users in the app, songs, which will store the songs in the music database, artists, which will store the artists in the database, and time, which will keep a record of the timestamps of song plays broken down into specific units. So here we can see our schema and we are going to create a star schema and this is how it's going to look. So in the song plays table, as we have seen, we have these columns, and then for the users we have the user ID, first name, last name, gender and level. For the songs we have the song ID, title, artist ID, year and duration. For the artist, we have the artist information like artist ID, name, location, latitude and longitude. And for the timetable, we have the start time, hour, day, week, month, year and weekday. Now the reason that we are using a star schema is because it allows simplified queries and allows fast aggregations. The tables are structured in such a way that the members of the analytics team will be able to quickly identify the total number of songs played by a user using just a single join. Similarly, they could also return an artist's most popular song with just 2 joins. So as you can see here that we can create optimized queries. So this is the star schema that is consisting of the fact tables and the dimension tables. And the SoundCloud analytics team wants to use this schema so that they can easily query the data and quickly output aggregations. So now let's move ahead and let's start writing queries for our tables. So in cell 1, we'll create a fact table called song play. And for that, we'll set the song play ID as primary key. And this would be of serial type. Then it will have other fields and we have mentioned the data types for each field. Then we create a user table and here the user ID will be the primary key and it is of type int. Then we create the song table and we will keep the song ID as primary key. Now this will be a varchar. Then we have the artist table and we have the artist ID as the primary key of data type varchar. Lastly, we have the time table and we will have start time as big int data type and we will make it the primary key. So now once we come to cell 2 and once we have created our queries and we have assigned them to our variables, now it's time to write the drop table queries. Now these drop table statements will come in handy when we need to establish our connection to the database again and again for testing purposes, or if we need to drop the tables quickly and start the project again. So in those cases, these queries will come in handy. So for the 5 tables, we have 5 drop table queries. and we use the if exists to check if the tables are already existing, and if they are existing, we will drop them, and if they are not existing, we will not drop them. Now moving ahead to cell 3, we will put all these queries in a list so that we can execute them using a for loop instead of individually executing them. This will help us avoid redundant code, and you will see ahead it makes our code much cleaner. So now let's come to cell 4 and we will create a function drop table, and once we call this function or method, we will be able to drop our tables quickly with just one function call. So as you can see here, we are looping through the drop table queries and then we are executing them one by one using the cursor.execute and connection.commit for committing the transaction. So here you can note that till now we have not connected our Python with the PostGRE SQL. We are just laying the foundation and setting everything up so that when we connect to our database, we just need to call the functions and we have our ETL pipeline ready, and the data modeling will be done with just a few lines of code. So this way our code will look more modular and clean. Now in cell 5, we will do the same thing as we did for drop tables. We will make a create table function, and this will help us creating the tables quickly. So now let's come to the ETL process. Now in this ETL part, the first thing that we want to know is what is ETL. So it is extract, transform and load. It is the general procedure of copying data from one or more sources into a destination system. This process has 3 stages. The first one is data extraction. So data extraction involves extracting data from the source. In our case, our source would be the JSON files. The next stage is data transformation. Here we process our data by doing data cleaning and transform it into a proper format that will be helpful for querying and further analysis. And we will be doing this shortly and you will see more about it. Finally, the last stage is loading the data. Data loading describes the insertion of data into the final target database or a data warehouse. So in our case, our final destination is the PostGRE SQL database, and we have our star schema for that. So now let's come to cell 6. Here we are going to import our packages and libraries. Then in cell 7, we will write a getFiles function, and what this function essentially does is it gets all the files matching to the extension from directory, and so in our case we want the JSON files. So what it will do, it will take an argument file path, and the file path is where our data is stored. So in our case we have 2 directories, song data and log data. So file path is where these 2 directories will be stored, and then what it will return is it will return a list of the paths to the individual JSON files that are contained in these directories. So once we get the individual JSON files path, it will be very easy to manipulate them using pandas. So once this is done, now we process our song data. So in this first part, we'll be performing ETL on the song data, and we will use it to create the songs and artist dimension tables. Now in the ETL, what we are going to do is we will load a single record into each table at start. We will make use of the getFiles function to get a list of all the song files that are stored in this path, and then we will select the songs, we will read the song file, and then we will view the data. So let's come to cell 8. So here, as I told you, we will call the getFiles function and we will pass in the path where our data is stored. Now coming to cell 9, let's just take a look at one JSON file and see how the data looks. So what we are doing here is that we are getting the path of the file and we store it in the variable file path, and note that we are just accessing the first element of the list, that is song files of 0, because song files will have all the paths to our files, but we just want to check one file path. Now what we do is, in cell 10, we make use of the read.json function and we'll pass in the file path, and what it will do is, it will read that file. So we go ahead and do df.head, and we see that we have one row of data. So now what we want to do is, we want to extract the data for our songs table. So we come down here and we see that in our songs table, we have the columns song ID, title, artist ID, year and duration. So we want only these columns. So in cell 11, what we do is, we filter out our data frame and we get the values in the song data variable. So note that here we are using .values of 0, and what this will do is, it will just select the values from our data frame, and what of 0 will do is, it will just select the first row of data in our data frame. So now let's come to cell 12. Here we are going to create our song table insert query. So what this will do is, it will help us to insert the data into our database. Now we move on to the second table. So we move on to the artist table. In the artist table, we have the artist ID, name, location, latitude and longitude. Again, we do a similar kind of a thing, and we are going to filter our data frame, and we are going to choose only the columns artist ID, artist name, artist location, latitude and longitude. And then again, we are going to apply dot values on it, and we will take the first row of data. So this is going to convert the array to a list and then set it to the artist data. Now once we have done that, we come to cell 15 and we are going to create our artist table insert query. Now this is nothing new. We have already seen this in the demos. So this should be pretty straightforward. So let's move ahead. So what we saw is, from our song data JSON files, we got the information about songs and artists, and as per our schema, we have extracted and processed the required information. Now note that here we are just using these cells to get a feel for our data, and later on we'll be writing the functions to automate this process of getting data from JSON files, transforming it and putting it into the database. But for now, let's move on to processing the log files data. So with the help of log data, we will be getting the data for our time table, users table and the song plays fact table. So once we come to cell 16, what we will do is, we will get all the file paths to our log data, and we'll do this by calling the getFiles function. Now we come to cell 18 and we are going to read the data in our JSON file. So we do a df.head, and here is how the data looks. So now let's move forward and extract the data for the time table. So here what we are going to do is, we are going to filter the records by the next song action. So in cell 19, you can see that we have queried our data according to the next song filter. And we are filtering by next song because it's synonymous to the valid plays where length of play is not none, and this should be synonymous to the count of songs. Now we come to cell 20. So as we know that our time is in timestamp format, and we are going to convert it to datetime format so that we can easily extract the different elements from the timestamp using pandas. So in cell 20, we will first convert the timestamp to date time. Now remember that in our table, we have the start time as big int, right? So first we convert the timestamp to date time so that we can extract the values for our other columns also. Like we want to store the hour, day, week of year, month, etc. into our table, right? So we will make use of dot values to get the value from the data frame without the index. So here you can see that we have used dot values to extract the information from the timestamp. Then in cell 22, we store our data in the time data frame. You can see that in the output of cell 22, we have our data cleanly displayed. It is in the format ready to be inserted into our timetable. So now in cell 23, it's time for us to write the insert query for our timetable. And here the thing to notice is that we are doing an onConflict on start time, and we say that if there is a conflict, do nothing. So the thing to note here is that why can there be a conflict on start time? Now after making start time as a primary key in timetable, we will have to handle the conflicts using the onConflict clause to prevent insertion of duplicate times, and this will cause an issue and it will prevent insertion. In other words, when we are trying to insert time points into the time dimension, we just have to ignore those new records where timestamp is already present in the table. So let's go ahead and move on to the users table. Now this is pretty straightforward and we don't need to do any transformation here. So we just need to filter our data frame for the columns of user ID, first name, last name, gender and level. Now in cell 25, we will write the insert query to insert records into our user table. Now one thing to note here is that we are doing an onConflict on user ID and we are updating the level. We do this because from our schema design, there is no unique constraint of user ID in the songs placed table, which means that multiple values in the field should be accepted. So we make use of onConflict clause to ensure that no duplicates are added in a case, say when a user upgrades from level is equal to free to level is equal to premium. Also, the onConflict statement needs to be set on the dimension table rather than the fact table, as the information relating to the level field is defined within the dimension table and not on the fact table. So now once this is done, let's move on to our fact table, that is the song plays table. Now this one is a little bit more complicated since information from the songs table, artist table and the original log file are all needed for the song plays table. Now since the log files don't specify an ID for either the song or the artist, we'll need to get the song ID and query ID by querying the songs and artist table to find matches based on song title, artist name and song duration time. So what we do in cell 12 is we first implement the song select query to find the song ID and artist ID based on the title, artist name and duration of the song. And then we create the insert query for our song play table. Now we will see the Python code later on to see how we find the song ID and artist ID based on the title, artist name and duration of a song. But for now, we have laid the foundation. We have made the queries for creating our tables, inserting the data in them and dropping the tables. We have also got a feel for our data and how it will be extracted, transformed and loaded into our database. So finally, it's time to bring everything together. So in cell 27, we'll create a function that will help us connect to our Postgres server and getting our cursor from it. We will use it to drop any tables that exist as we want to start fresh every time. Then we'll create our new database called SoundCloudDB and we will close the connection to our default database. So as you can see here in the return statement, we will get back the cursor and connection to our SoundCloud database. Now in cell 28, we make a function to process the song data files. In the previous cells, we had seen how to do an ETL, and it's time to make a kind of a pipeline and a structure for the whole process. So as you can see here, we are reading the JSON file Then we are getting the values by doing a dot values, and then we are converting them to a list. We are doing this so that we can easily insert the data into our database. And then what we do is we execute the query. So we execute the insert query with the song data. Now we will do the same thing for the artist data. We extract the values, we convert it to a list, and then we'll execute the query for inserting data for the song artist into the artist table. Now let's come to cell 29. Here what we'll do is we will read the log data JSON files, transform the time data, and this is all the things that we have done before. Then what we will do is, using the for loop, we will insert data into our time table. So as you can see here, we are using a for loop and we are executing the time table insert query and we are inserting the data. So these are all things that we had seen earlier also. We do the same thing for the users table. So as you can see here, we have got the values and now we are inserting the data using the for loop over here. Now coming to the end of the cell, we see that we execute the song select query. So here is our song select query, and what this will do is it will find out the song ID, artist ID based on the song title, artist name and song duration. And if we find those results, we'll assign it to song ID and artist ID. If we don't find it, we will assign none to them. And then what we can do is we'll insert our song play data into the song play table by executing the insert query. Now all this code might seem a little bit overwhelming, but we have seen the step-by-step process and it's looking a lot because of the comments. So don't worry about it and don't feel scared. So now let's move on to cell 30. Here we are going to make a user-defined function called process data, and that will get our file paths from the song data and log data directories, and it will call the above two functions that we created for processing song file data and processing log file data. In the last line, we can see that we are printing out how many files have been processed. This will just provide us with a status update. So now let's move on to cell 31, and this will be kind of our main function, and this will control the code in the whole notebook. You can say that this is a kind of a main function from where we'll make calls to different parts of the code. So first, let's go ahead and make a connection to our database. For that, we'll make a call to the create database function. And what this will return is, it will return the cursor and connection to the SoundCloud database. Then we'll call the drop tables, and then we'll call the create tables function, and we will pass the cursor and connection so that our tables are created. Now once we are done with that and our tables are created, we want to call the process data function. So now we will call the process data function and pass the arguments. So in the first process data call, you can see that we want to process the song data, and thus in the function we have passed process song file. Now in the second process data call function, we will pass the process log file function so that we can process our log data files. So what this will do is, it will read all the JSON file paths from song data, extract data from JSON files, transform it and load it into our database tables. Similarly, we will call the process data function again to process the log files, and it will read in all the file paths for log data. It will extract the log data from the JSON files, transform it and load it into our database tables. And even in the output, you can see here that it says that there are around 71 files that are related to song data, and we can see here that there are about 30 files for the log data, and it shows us an update as each file is being processed. So now when everything is done, it's time to validate our data models. How can we be sure that everything is working perfectly and our database is ready to provide us with the analytics? For this, we will need to query our data. So now coming to cell 32, you will need to uncomment this first line to install the IPython SQL library, and you need to uncomment it when you run the code for the first time. Now what this will do is, instead of writing Python code, we will be able to query our data in the same way like we would do it with the PostGRE SQL shell. So we can write SQL style of code right here in the Jupyter notebook. Then let's come to cell 33, and here we will load the SQL extension. Now in cell 34, we will connect to our database. The format here is that we write PostGRE SQL and then comes the username. So in my case, the username is Postgres. Then we will write the password. In my case, it's my first name. Then we write the localhost, and then we write the database name. And that in our case will be SoundCloud DB. So in cell 35, let's run our first query, and what we'll do is we'll check to see if our data is correctly inserted into the users table. And so we'll do a select star from the users and we'll limit the results to 5. So as you can see in the output, the data has been correctly inserted. Now let's run another query in cell 36 and we will check if our data is inserted correctly into the songs table. And we'll do a select star from songs and we'll limit the results to 5. So as you can see here, the data has been correctly inserted. Now in the same way, we'll do it for artists and we'll do it for time tables. Now let's come to cell 39. So in our database, there is only one record in the songs placed table where the artist ID is not null, and thus to check if everything went well, we will execute this query. So our query is select star from song place where artist ID is not null, and we'll order by the artist ID and we'll limit the results to 5. So as you can see here that we got only one row, since only one such row exists, and now we can confirm that everything went well. So now here on cell 40, cell 41 and cell 42, I have provided you with 3 queries on which you can practice, and I encourage you to create more queries of your own and try to do some analysis. So at last, in cell 43, we'll close our cursor and we'll close the connection. And so this will end our demo for today. So in this lecture, we learnt about data modeling with PostGRE SQL. We saw normalization, denormalization. We saw the different schemas like star schema and snowflake schema. And we also went over a project demonstration that tells us how to model the data using PostGRE SQL. So this ends our lecture for today.